Okay, good morning. My name is Salvatore Coffa from STMicroelectronics. As already said in the introduction, I will talk more about manufacturing of this device. Specifically, in my talk, I will, of course, introduce the big advantage in power devices of also silicon carbide and gallium nitride power devices. But I also give an introduction on what are, from processing and manufacturing point of view, the challenges also for silicon power. Then moving to SiC and GaN, basically concentrating on the main difference that you need to do in the flow, specific equipment or specific process that you normally don't have in the silicon part. Having said that, a few words about the main trends in power semiconductor. So power devices transform energy from one form to another. So you find them everywhere. You need to take energy from, for example, a battery, and then drive electric motors, or from the main and driving an electrical motor of any form. And the name of the game there is that basically this conversion of energy and power should be done in the most effective manner, without losses and without wasting power just for the conversion itself. The market of this device is huge and is getting larger and larger every year, mainly driven from some transformation in our ecosystem, coming from electric mobility, for example, electric car, or 5G interconnects and communication, and few others. It calls for each time for more efficient, more small power devices able to perform very well at high current, high frequency, and high power. Of course, you can cope with this in different manner.
Sure. Good.
You can use, of course, silicon. We use a lot silicon. All the semiconductor manufacturers use silicon a lot. High voltage motors, silicon IGBT for many applications. And more recently, for application going, say, to very high power, medium frequency silicon carbide devices has come into the play. And for application in which we have medium power, low power, and especially very high frequency operation, GaN transistor perform much better than silicon. So this is the main driver toward, say, compound semiconductor versus silicon. Okay, having said that, some really basic on semiconductor manufacturing. I will spend a few times on the slide. Of course, the semiconductor manufacturing is about, say, at the end, having in a package an IC or a discrete device which has been fabricated on a wafer. How you do this? Well, first of all, you have to make your initial substrate, so your initial wafer. So, of course, also in silicon, you have a lot of ingot growing. Most of this in today's semiconductor manufacturing is done by a company which are outside the semiconductor manufacturer. So we buy the wafer for silicon for the semiconductor manufacturer. Then basically you make your design of your device, so you understand what the structure should be, and then using a variety of process, you go to the front end to actually implement on the substrate this structure that you have conceived. And finally you go to the back end in order to connect to the external world. So in a nutshell, the process that we are familiar with in the production of a silicon, generally a silicon device, is the grow epitaxy wherever is needed, in the power is needed, thin film deposition by a variety of means, and thin film means dielectric, means metals. Litho, a lot of litho in order to define the feature that you want to achieve on the surface, ion implantation for precise positioning of the dopant and controlling of p-type and n-type doping layer, thermal process for activating the dopant, plasma etching. All in a clean room environment, of course. And going to the process flow, you start from the wafer in. You do, for example, film formation, like it can be the epitaxy, it can be the deposition of a dielectric, for example. Then basically you make a lithography, so you define exactly the structure that you want. You do some etching in order to remove the part which should be removed for fabricating your structure. Then basically again you go to ion implantation doping, and then you thermal treatment, and you repeat the process depending on the complexity of your devices several times in order to achieve very complex structure like this, for example. So all of this is being realized by what is called front-end process with a variety of steps that I described to you. These are very consolidated in the silicon technology. And also in the silicon technology, one thing which is, I think, is important to underline, especially in this context, is that basically we've been in the last 30, 40 years introducing progressively new material. It's a lot of material work in this world. For substrate, silicon carbide, gallium nitride, but also for the electric, but the high K, low K dielectric, various methods of depositing film with specific properties, and polymers, photoresist, and whatever, metals, noble metals, and so far and so on. So there is a variety of process and material which has been continuously introduced in the last 30 years, even in the silicon process. All of this is an environment which is a clean environment in which, of course, you have to take care of contamination, particles, and so far and so on in order to have a working device at the end of the day. So this is the general, but let me say that basically since the beginning it's been clear that there is a significant differentiation between those processes that goes, let's say, with more Moore, what was more Moore before, so DRAM, CMOS, and other stuff in which you introduce progressively new nodes. At the beginning, it's not that much right now. The beginning for 50 years has been characterized by introducing a finer and finer node, so a smaller and smaller dimension by advanced lithography. Smart power, that follows the same path with some delay in time. And power discrete or power electronics, which has been always different in the sense that basically innovation from one step to another, of course, has been driven by lithography, but not only by lithography. It has been driven also from the way in which you make the structure of the device and the material that you use, the so-called more than Moore approach, not only litho. And so I will concentrate more on the power in my presentation. Okay, some difference. If you go with, say, CMOS mainly, you have the standard substrate, you have typically thin layer, and the temperature process is minimum. So there is not very high temperature processing of the device. The final thickness, at least final thickness after all the steps has been done, is basically standard. If you move to power device, you have different things to take into account. First of all, the use of epitaxy, of course, much more than the other time. You use typically thicker layer. You have an high topography in the structure. You have long diffusion time, high temperature process. You have to use and manage in the manufacturing thin wafer technology. So bringing the wafer down to, say, 40, 50 micron, but still having some of your front-end process to be performed after the thinning, which is not common in CMOS. You have to withstand high voltage, high electric field, and introduce, as I said before, new materials progressively. So in a power device, in silicon, you normally have a very simple structure like a planar device in which you have your gate oxide, so you have your channel here. So basically you turn it on and off with the gate, the channel, and then you have a current flow from the source to the channel vertically to the substrate. That's how a power device works. So if the channel is closed, not open, you have a low on resistance. If the channel is closed, you have a high blocking voltage because you use this thick this thick epitaxial layer in order to withstand the electric field. Note that basically in the case of power, based on silicon, well, of course, we have by definition a very good gate oxide with a good interface properties. That's, I mean, the name of the game for the silicon has always been silicon oxide with outstanding dielectric properties and outstanding interface properties between silicon and silicon oxide. And typically, you start from a substrate which is completely free of defects. There is no dislocation. You make epitaxy which is free of defects. So whatever you do, if there are defects, this is a defect that comes in your diffusion line. It's not the pre-existing defects. I'm telling this because when, of course, we move to silicon carbide, we have a different story. Let me say a few things about the manufacturing of silicon power device. Over the year, the structure has changed a lot. So, just to give you an example, in all of this, the surface is here. Most of modern power device has a trench structure in which the gate oxide is in the wall of a trench. So a really three-dimensional structure in which you have a lot of etching, you have a lot of litho, a lot of things to control. And also in the case of very high voltage device, you have this three-dimensional structure. This is fully crystalline, but you have P-type doping going up to 40 micron for a 650 volt device, immersed in N-type in order to have a 2D electric field and getting better on resistance, better performance. In the case of IGBT, you have to manage a gain range, and we have to manage also thinning of the wafer before the final step on the back. So some not limiting characteristic of the silicon power device processing is the fact of controlling thin wafer, because after thinning, as I said, to 70, 60, or even 40 micron, still have a lot of process to make on the back. You have to clean, to wet etch, you have to do lithography, you have to do ion implantation for the emitter of some of the device, you have to do the dopant activation with the front already formed, and you have to deposit layer and to make the final metal of the device. Of course, the dopant activation is a significant part, and this has been solved over the year by the fact that the dopant activation on the back, after that you perform after the front metal is already on place, so it cannot go high in temperature, is done by laser annealing. You use a very short laser pulse, so you can heat the dopant on the back without a significant heating of the device on the front. And all of this today is in any of the manufacturer of silicon power device is in full production in the manufacturing flow. Now, having said about the silicon, let me move to silicon carbide power devices. First of all, why we want wide bandgap? Well, this is again because of properties of the materials. If you look at electrical, electronic properties of the material, and you compare silicon, which is here, to silicon carbide, which is this one, and to gallium nitride, which is this one, well, I would say from the point of view of power, I would choose not silicon as a first choice, because you have an higher bandgap, an higher electric field in the compound semiconductor, a better thermal conductivity, especially in the case of silicon carbide, a better electron velocity. So whatever application needs high voltage, high power, and fast speed, certainly will have some benefit from the compound semiconductor. Of course, you have to pay something. In life, you always have to pay something. And the something is that basically the technology of silicon is there from 40 years. The material properties are understood and under control. In the case of silicon carbide, the gallium nitride, this is still an ongoing work. But the reason why everyone, including us, is pushing for silicon carbide can be summarized in a very simple thing. This is an important figure of merit of the device, which is the specific on resistance. This means when the device is on, it would like to act as a perfect switch. It's on without losing power. So the higher is the on resistance, the more losses you have. And this is the evolution on power in silicon. This was a planar MOSFET. Then we introduced the three-dimensional that I was describing before. So the first jump is going 3D. and you give you a significant benefit in the own resistance. But let's see what happens if you instead using a gain planar, but in silicon carbide. You already have a big jump, and this is progressively going down. So this is the reason why people in the world start studying the defects, understanding how to control the defects, how to make wafers over wafers, first in 100 quantity, now in 10,000, 100,000 quantity, because the benefit is huge. And as always, in the story of technology, let me skip this, it has been a story of hype cycle. So at the beginning, it was when silicon carbide, first silicon carbide device was shown in some labs, everyone was enthusiastic, like saying, this is going to change the world. Then basically you reach a peak of expectation, then nothing happened, because frankly speaking, for 10, 15 years, the market was not dominated by silicon carbide. Then basically something happened, in some cases this happened, which is when some application really badly need the new technology. It doesn't matter if it's more expensive, it doesn't matter if you have to take care about the reliability because you have defects. The benefit in the application is so huge that some early adapters want to use them. So you move from, let's say, 100 wafers per year, 4-inch, to 5,000 wafers per week at 8-inch. And that's because the technology can solve in a different manner some problem. One of the first problems the silicon carbide was able to solve is the fact that basically when you take one specific application, you want to power the inverter, the electrical inverter of the inverter of electric motors. Of course, in electric motors, you take the energy from the battery and you drive your car. The more you consume in this transition, the less the battery will last. So if you show like this, that the efficiency of the transformation of energy from the battery to the main inverter, using silicon carbide instead of using a traditional silicon power base is much better. This means that you will have either extended mileage with the same battery pack, or you can reduce your battery pack for the same mileage. And this was what started the first mass manufacturing of silicon carbide. So the fact that basically in this application, this was considered winning. Then, when this happened, the market also considered several other applications, both in the industrial and in the automotive, more and more in the automotive arena. But it was necessary, again, to start with, because if you start with that, then basically all the supply chain will adapt to the need of more devices. As I said, and of course, now it is extensively used in the electrification of the car, not only the main inverter, but also in other parts, in other electronic components of a modern car. Of course, as I said to you, you always have to pay. Nothing is for free in life. And the point is that basically, if for now this is not anymore silicon, but is silicon carbide, well, then basically the substrate is not free of defects, the epitaxy is not free of defects, and also the surface of your device, if you etch, show you defects. So you have to be careful, because these defects, of course, can be, through the proper EPI process, be mitigated. The number that we transfer from the substrate to the EPI is fortunately reduced, but defects still can be formed. So when you are here in the gate oxide, in forward and reverse bias, you can have a combination of defects at the interface between silicon oxide and silicon carbide, and you can have high electric field. Because remember that we use today silicon oxide again. So you have the same gate oxide material, but due to the properties that I was showing you before, now your maximum electric field that silicon carbide can withstand is 10 times higher than silicon. So while in silicon, at this interface, you can have something like 2 × 10⁵ volt per centimeter, now you can have 2 times 10 times to the 6 volt per centimeter. So you have to be very careful about power. Talking about defects, this is a comparison side by side of silicon and silicon carbide. Of course, 0 defects in the main substrate, 0 defect in the epitaxial layer. Silicon carbide, of course, good dislocation, basal plate dislocation, lot of dislocation in the bulk. Whatever you do, you can reduce this concentration, but cannot go to 0. And then basically, when you go to the epi, even with the best epi process, you still have some transferring of these defects or some transformation of the defect of the substrate that generates defects in the epitaxial layer and then in the active area of the device. They are called error, triangle, second fault, whatever. Okay? So defects means that the topology of your surface will look like this. This is a carrot crossing the strip of the power devices. This is as a triangle, again, showing up on your surface. These are killer defects. So these defects produce you 0 electric yield. So it cannot yield. The device is not working. Let me say this is annoying, but it's not the most worrying part in silicon carbide. So you need, for silicon carbide manufacturing, you need to do something that is not done anymore by the semiconductors, which is the substrate, which is controlling the defects of the substrate and the properties of the substrate. Because depending on how you grow, you can have effect on the resistivity along the bull, which impact on resistance, but also the distribution of stress in the bull itself. You have to control the flatness, because if you don't have the flatness, then when you go to the front-end process and the lithography, you have problem for focusing, for the focus of the optical lithography, and you have, of course, to control the defectivity. So you have to make specs that allows you to yield your device. This, if you buy from outside, is a spec that the provider has to guarantee to you, and then you check this. If you produce inside because you are an integrated manufacturer, then basically you have yourself to guarantee that this is the case. So you need to control this. For controlling this means a lot of tools that are progressively becoming more and more fine-tuned for controlling the resistivity, controlling, of course, the topology, see if there is bow or warp or local thickness variation, which is really a very important problem. So the manufacturing, before even starting the diffusion of the first step of the deposition lithography, has to consider this at substrate level. And in the subset, you have to measure the density of dislocation, because you have to achieve a spec. You measure it typically by a destructive method, which is KOH. And of course, you can also have statistics, and it's also very expensive. And more recently, of course, there is an introduction of things like tomography, X-ray tomography, in order to have a non-destructive manner. But the point is, if you want to manufacture silicon carbide, you have to have a way to control the growth of the crystal and to measure the defectivity, warpage, and resistivity of each and every wafer of the board. And then basically, if you go to epitaxy, so you now grow a layer on top of the silicon carbide, and you make some transformation of the defects. Again, you have to measure, of course, the thickness, because in a power device, the thickness and the resistivity of the epi layer basically determine the voltage class. You have to make the thickness, you have to measure the doping, and we have to take into account the uniformity of the doping, which is another point to take into account. And of course, you have to inspect defects. So each defect of silicon carbide after epi that introduced in the line is measured by typically optical method with scattering of the light and also photoluminescence in order to have a map of each and every defects which are on the surface of your device. Because this is important for the control of the process, for the control of yield, and the control of reliability at the end of the day. So it's something that in the silicon-based technology, silicon power-based, this we don't do. We assume and we know there is no defects to start with, okay? Here you have to measure, making sure that you are okay. Then, once you have done that, well, first of all, I said there are some defects which are killer defects. So in AWS, the yield on that specific device is 0. So the device is not working. This means that depending on how many defects you have on your EPI, your yield will depend on the area of the device. The smaller the area, the higher is the yield. The smaller are the defects, the higher is the area in which you can have a good yield. So if you want to make 30 millimeter square silicon carbide, we are about here, then basically you have to make sure that basically it should be in the low range of defects. Otherwise your yield, just for the fact that these defects are there, will be very low. So as you can imagine, the material study on the subset and the epitaxy is continuously improving the properties. So today we are well below 1 defect per centimeter square on the surface, and basically we are progressively going to 110 per centimeter square. In some cases, some killer defect has been completely eliminated. Having said that, you cannot stop because the application is there. So basically what we do, in order to make sure these defects, some are killer, some other are not causing electrical failure, but can show up in the reliability. So in order to guarantee the reliability in the final application, we have to do a lot of screening of the initial defects and a lot of burn-in. So basically all the part that comes to the end are submitted to an accelerated test in order to eliminate those parts that will give otherwise early failure in your application. And can you imagine in a car, in a car application, this is a fundamental point. So along the line, we've done a lot of study, understanding, for example, things like that basically some of the defect that does not show in the yield, like what is called threading screw dislocation, is one to be taken seriously into account. That's how it appears in your device. Is a dislocation coming from the subset, reaching the interface between silicon carbide and gate oxide, and produce electric field crowding here, which then can be responsible for oxide failure during the application. So you have to eliminate these defects from the final product. Having said that, of course, how you cure this? It's very simple. You do some material study in order to get to better and better substrate and EPI. You also make a design for manufacturing. So basically, moving from generation 1 to generation 2 to generation 3, we have modified the structure of the device so the electric field at the interface between silicon carbide and gate oxide is progressively smaller and smaller. Typically, in a gate oxide, reducing the maximum electric field of 1 megawatt per centimeter gives you 2 orders of magnitude in the lifetime of the gate oxide. So it's important that you do this. The other thing that you can do is, of course, getting vertically integrated, which is something that we did in 2019 through the acquisition of Nostell, which is now STAE. So that basically we are also able to produce internally our stuff at 6-inch at 8-inch. And you understand that more than being just connected to the availability of the wafer or the cost of the wafer, it's also linked to the fact that this is going to control the performance of your device. So while in silicon you have a standard of subset or subset plus heavy that you can buy from outside that goes without defects, this is not true for silicon carbide. This is one of the main differences today in the manufacturing flow. We are vertically integrated, I already said. We are going to use as well, we've been participating to transform the smart SiC for producing more wafer of silicon carbide. Let me say a couple of things still concerning silicon carbide. Okay. In silicon carbide, one of the issues of ion implantation is linked to the fact that basically in silicon carbide, the dopant does not diffuse. So you can make thermal process, but there is no diffusion. While in silicon, the shape of your junction is determined not only by the implant, but also by the diffusion. In the case of silicon, the entire shape of the dopant pocket is determined from where the ions are put by ion implantation itself. So if you want to do 1 micron thick p-type, for example, you need to make several implant because you cannot diffuse. So you have to put the dopant up to 1 micron. So in silicon carbide, it's getting more and more important what is called implant in channeling condition. So instead of implanting in a random direction, you implant through the axis of the device. And compared to random, which is the green, the ion implantation, the channel ion implantation, this is true also in silicon, by the way, but in silicon carbide is even more important. It can go much deeper and with a distribution which is more flat. So it's a law that ion implantation in channeling condition is a very important technology for silicon carbide. It will be used more and more in the near future. Also because if you combine this with very high voltage, you can see that basically you can go as deep as 5 micron. And the only way in which you can reach this depth is by using channel ion implantation, because there is otherwise not enough energy, and again, as I said before, there is no diffusion in silicon carbide. Skip this, and if I still have 15 minutes, okay, before the coffee break, I will move to the GAN. And again, the idea is trying to give some idea of what is different in terms of manufacturing. Always for power devices. Some of this has been anticipated by the previous speaker, so I can be even faster in some of stuff. First of all, let me say that basically here today in ST, we are talking about the lateral high electron mobility structure. So this means that basically we are not using vertical at the moment. So use devices in which, first of all, the GaN is grown on a silicon substrate. So what I will present is about GaN on silicon. Then, of course, due to the properties of the G5, you end up having this situation here in which at the interface between the GaN and the GaN, or anyhow the barrier, you have a 2D natural electron gas due to the polarization effect and the difference in the band gap. The 2D gas has an important properties, which is has a certain density, and especially the mobility is very high. Because while in silicon, typically the doping, the electrons are associated to phosphorus or arsenic ions, so you have the scattering due to the positive or negative charge dopant ion. Here, these are free electrons, so there is no associated scattering. So this mobility can be as high as 10,000 centimeters square for volt per second. The important thing is that basically this combines the benefit of high band gap, so like in the case of silicon carbide, you can go to reasonably high voltage within the layer. And of course, in this case, you combine also with the fact that you have very much reduced capacitance. You have no junction to deplete. But in the case of the conventional MOSFET, you have a lot of junction that basically give you parasitic effect. The result of this is that basically here is just to show some of the structure that we have already fabricated. So it's, I would say it's a standard flow, taking into account some main difference in the case of GaN are important, which I will mention in a moment. Again, let me argue about the reason, because this stuff is very worrying, because you have the epitaxy, which is an heteroepitaxy with a lot of trading dislocation. You have surface, a lot of surface. This is a lateral device. So the status of the surface, if you have traps at this surface, is affecting the performance, dynamic performance, static performance of your device. So it's really a pain in the ass, let me say. But again, and also from the reliability point of view, there are a lot of groups that are working on this. But when you look at simple application, there is no story. If you take this, it's just a non-limiting example. Take a DC-DC converter and again look at the efficiency between silicon-based and gallium nitride base, especially if you want to increase the frequency of operation. And increase the frequency of operation in the final application is beneficial because it reduces all the inductors, all the magnetics and other stuff. Well, it's complex from material point of view, but in terms of performance, if you go, say, above 500 kilohertz, there is no story. You can do things that you cannot do with silicon. So that's, again, why people are considering going to application and to volume manufacture, also in this early time from the point of view of material properties. The application, I mean, there are many of them. Some of them are in the car, some of them are in telecom, some others, especially for RF power, are in the communication, of course, which is a lot of use of GaN for power amplifier for base station. Okay, let's concentrate on the power. On the power, basically, one of the problems that you have with the nice structure that I was describing you before is that structure is typically normally on. So you need a negative voltage in order to turn it off. So if you want instead to have something which is normally off, like is required in many of the power, or some of them at least, you have two possibilities. One is to undergo the pain of growing also P-type, so you make then junctions that control here the gate and eliminate the 2D gas at voltage, at gate voltage equal to 0, so that you can have a normally on device, or you go through a recess in which you basically have an amp and you combine this with a MOSFET. Each one of them has advantages, disadvantages we can name that. We have chosen, for example, that we're bringing to the market device based on P-type that shows indeed the advantage that basically I was telling you before in the DC-DC conversion. But now, one other point that basically was mentioned is probably in some of the questions before, and which is important, is that basically the lateral structure, in which basically the current, as you remember, flow from the source to the drain on the surface, allows you also to make some integration. Easy. So you can combine also with logic transistor, with depletion and enhancement transistor, so you can create something which is a monolithic GaN devices based on gallium nitride layer on a silicon substrate. Again, what we need to pay? Well, when you look at the structure, there are a couple of things. The first thing that I will mention is epitaxy. You grow this on a wafer of silicon, and of course there is a large mismatch in the lattice between the GaN and the silicon, and you have a large mismatch as well in the CTE. So whenever you go to high temperature, you go down, it's a lot of stress. So you have to manage your epitaxy in such a way that you have something which is flat enough at the end of the day to be able to go through the existing line. And a variety of other things that concern the way in which you control the properties of this surface, avoid to introduce traps by the process itself. So the way in which you passivate the surface and etch the surface is particularly important. I would say that these are the two main points, the way in which you control that you have low defects at this interface or low electric field at this, and the way you manage your epitaxy. The third point is the fact that gallium nitride is not prone, it's not able to sustain a very high temperature process. So be careful on what are the processes that you use in your ohmic contact, in your processing, if you try to activate dopant, because otherwise you have the composition of the material. So say above 800 degrees with RTA, it's not possible to go, which is completely different from what happened to silicon and silicon carbide, in which the case of silicon carbide, you have dopant titration at 1,700 degrees, for example. Having said that, I'm going to conclude. Yeah, of course, whatever you do in your epitaxy, so the silicon substrate is here, so you have a lot of multilayer and other stuff which are used to manage the stress that you have and to reduce whatever gets to the surface. Still, you have some threading dislocation going up and reaching your active part of the device. So once again, you need to have an internal work, because you cannot just buy epitaxy from outside, because if you buy by outside, you cannot control your destiny in terms of these defects. And especially, it's been proven by several groups, including ours, that the loop in the gallium, this kind of device, you have a continuous loop between the device structure and the epi. When you make true optimization step, you optimize both the device structure and according the epi. You cannot decouple the two, so you need to control both. Otherwise, you lose a very good node in your design capability. So again, you have to control the condition, you have to control the stoichiometric composition. See how complex it is, especially on silicon. Silicon, you have a buffer layer to reduce the stress. Then you have the isolation channel here, and then the barrier, and then again cap on top. And you have to control the composition. Here you have another thing that you need to control, which is the composition, because you have, in the case of YESvGaN, you have a ternary alloy, in which the concentration of aluminum, the distribution and uniformity is affecting the properties of the device. So you have also to do this. So again, in a manufacturing environment, you need, first of all, to introduce the possibility to make measurement characterizing the epitaxy from the point of view of the barrier, or the point of view of the bow, from making the XLD in order to see the crystalline properties of the layer, and of course measuring by contactless means the resistivity of the 2D gas that gives you the conductivity properties of your final devices. And last but not least, you have of course to map defects, because there is not such a process without defects. Defects can be cracks, can be area of high stress, can be pit. You have to map each and every defects with dimension that goes, of course, to large dimension like 20 or 30 micron, but also to very low dimension, especially in the case of P. And you combine again optical and structural process in order to have defined maps of this stuff. This is also completely different from what happened in silicon. So the metrology applied to you have the epitaxy, which is an MLCVD, and you also have all the metrology tools that goes with that, and the improvement that probably we'll see in some of the presentation after the break in the methodology for looking at these defects. Finally, and I'm going to conclude, and I don't have the time to go into detail, there is the passivation. Of course, the way in which you passivate the layer and you close the traps at the interface is very important. And here, the use of high KD electric, or the use of atomic layer deposition so far as on, is becoming very, very strong compared to the application that we have of the same methodology in silicon or even silicon carbide devices. So I think I can stop here. Probably one thing that, again, before the conclusion, one thing is that, for my kind of experience in the past, I used to be, more than 20 years ago, an ion implanter guys. So I like wherever possible to use ion implantation for doping. In silicon carbide, in gallium nitride, is difficult because of the problem of the activation. But there is a revamp of work about possibility by using capping layer or even high pressure during annealing, which is coming back. And I see papers, especially from Japan, which are coming up in order to understand if it's possible from manufacturing point of view to use ion implantation. My opinion is something that basically we are going to explore very much, because it gives you a freedom that normally you cannot get by only, in my opinion, you cannot get by only epitaxy. Okay, as a conclusion, I would say that basically it is true that basically silicon carbide and gallium nitride wide bandgap semiconductor in the field of power is becoming extremely important. So still you have a huge market for silicon power device, but you have a fast growing market of silicon carbide MOSFET already established and growing, and you're starting to see several applications in which gallium nitride power devices are introduced, and we'll see more in the near future. One thing from a semiconductor guy is that basically the thing I show is such that basically when you want to move one fab from making silicon power devices to silicon carbide to gallium nitride, you don't need to change everything. Because most of the process, I would say 85% of the process in silicon carbide and probably 90% of the process in gallium nitride you can do with existing equipment and the existing environment. Of course, you need to invest in those which are, let's say, basically distinguished feature of silicon carbide. The silicon carbide is the ion implantation, is the high temperature annealing, is the epitaxy, and of course the substrate grow if you want to be integrated vertically. In the case of gallium nitride, I would say it's mainly the epitaxy, plus some consideration on cleaning and passivation of the layer. This is very important. That's why each of the traditional semiconductor company, like ours, like others, are deeply involved in silicon carbide and gallium nitride. There is also the possibility to reuse existing infrastructure, and this is very important, considering what is the investment in a fab like that. I would say that from the point of view of application and reliability point of view, is something that requires some attention in terms of screening, also burn-in and other stuff, but it's something that can be granted also for application as delicate as automotive. Thank you.